In this video, I'm going to keep talking about 6.3 and do 2 examples, so you must watch the other video before this. So the example says, for each of the following functions, find formulas for the Maclaurin polynomials P0, P1, P2, and P3. Find a formula for the nth Maclaurin polynomial and write it using sigma notation. So remember that for the Maclaurin polynomials, the only difference is that a is 0. And I want to talk a little bit about a, right? So basically, whatever a is, we're approximating the function's values near that a. So that's what we're doing, is finding a series that approximates the function near that value. So since f of x is e to the x, and we know that the derivative of e to the x is just e to the x, then we know that, right, the first derivative of f is equal to the second derivative of f is equal to the third derivative of f is equal to the fourth derivative of x is equal to the nth derivative of f, right? It's all the same thing, e to the x. Then when we plug in 0, right, because remember, we want to evaluate the Maclaurin polynomial, so we have to plug in 0 for a, right? We know when anything is raised to the 0th power, then it's equal to 1. Okay, so, right, recall, right, our formula for the Taylor series, equivalently Maclaurin series polynomials, is f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus dot 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 up until we get to the nth term. So we do as many terms as, right, this n tells us to do. So fn of a over n factorial times x minus a to the n. Okay, so we need to find p0, and p0 really is just going to be f of 0, right, which we said that's just equal to 1, and then p1, right, that's just going to be the first term plus, now we plug in the n equals 1 term, f prime of 0 times x minus 0. So that becomes, we know f of 0 is 1, plus we know f prime of 0 is 1, so that second term is just x. Then we have p2, right, so we bring down those first 2 terms, and then we have to add on our final term, which is the n equals 2 term. Right, so then p2 simplifies to, this is just 1, this is just x, and then f double prime of 0 is just 1, and then 2 factorial is just 2, and whoops, this a is supposed to be a 0 here, so that just simplifies to x squared. And then finally p3 is, right, all those terms from p2, and then we need to add the n equals 3 term to the very end. So f triple prime of 0 over 3 factorial times x minus 0 cubed. So then p3 is, right, we have all of those terms from p2, and then let's look at the last term, which f triple prime we know is 1, and then we know 3 factorial. I feel like I'm going to keep it like that and keep this as 2 factorial. Right, because I'm thinking future oriented. I know I want a formula for Pn. And if I change this to 6, then that relationship between those terms isn't really clear. So I feel like I'm better off. Right, so this is really about pattern recognition, right? Because if I have it like this, right, my next job is to find Pn, right? So remember Pn we had right up here. Let me actually just copy that. Right here. Oops. Right, so we already have the first three terms. We have 1 plus x plus 1 over 2 x squared plus 1 over 3 factorial x cubed. And then when we think about this very last term, we know fn of, right, in this case we're doing a is 0, right? All of these really should have been 0 here because we're doing the Maclaurin series. Okay. So fn of 0 we know is 1, right? We set that up here because the nth derivative of f is still e to the x. And then whatever n factorial is, it is. And then we can just get rid of the minus 0. Right, so when I look at the terms, right, I'll notice that this here, this pattern here is more accurate than trying to rewrite this as 6, right? Because then I look at, I had a 3 factorial and the 3 exponent matched, and then I had a 2 factorial and the 2 matched, and then the n factorial, the n matched. Right, and then if we think about it, we could have had a 1 factorial and a 1 there. So if we want to write a formula for the nth polynomial, right, we see that we have, right, the sum from k equals 0 to n, right? I'm going to do that because n is supposed to be the last term in our sum, so I'm going to switch the index to k. Then we have 1 over k factorial times x to the k, right? So remember, I want the factorial and the exponent to match, and I want that to be the index that I'm on, right? This is k equals 1, k equals 2, k equals 3, k equals n. So that's how you do finding the formula for the nth Taylor polynomial or Maclaurin polynomial. Right, so this represents the function e to the x around 0. Okay, for the next one, we're doing f of x is sine of x, and it's the same thing that we're instructed to do. Hold on. So it's the same thing we were instructed to do for a, where we're going to find p0, p1, p2, p3 for Maclaurin, so a is 0, and then find the formula for the nth Maclaurin polynomial. So we know that we're going to need the first few derivatives, right? So what's the derivative of sine? We know that's cosine. What's the derivative of cosine? We know that that's going to be negative sine. What's the derivative of negative sine? Right now the negative sign stays, and the derivative of sine is cosine. And then what's the fourth derivative? Right, then we go back to sine. Okay, and then we're supposed to plug in 0 into all of these, and so f of 0 to start, we know sine of 0 is just 0. And then we know cosine at 0 starts at 1. And then we know, right, sine of 0 is 1, but now we have a negative sign. Am I tripping? No. Sine of 0 is 0, so that negative sign is irrelevant. And then f double prime of 0, the triple prime of 0 is, now we're back at cosine, so that's where the negative 1 is. And then when we're back at sine again, we get 0. Right, so every other one is going to be 0 because sine of 0 is 0. Right, and notice, like, because we came back to sine, we know this pattern is always going to repeat where the fourth derivative is sine. Right, so since the fourth, and that's why I wanted to go up to the fourth derivative, and usually with trig functions you get a pattern like this. So okay, so basically, like, all of these even ones are going to be your sines, and then all of these odd ones are going to be your cosine. And notice that cosine ones alternate between 1 and -1, so therefore we can make note of that, right? We can say that we know the even ones, which we know we represent even numbers by 2 times some variable, right? Because 2 times anything is always going to be even. So we know the even ones are sine, so sine of 0 is always 0. And then for the odd ones, remember, we represent odd numbers with +1 or -1 from 2 times a number, right? And that's going to be -1, and then the power is going to fluctuate, right? So we need to make sure we have that alternating sign thing there, right? So just remember, even numbers, this is like a side note, is represented by 2 times a variable, and odd numbers are represented as 2 times a variable plus or -1. Either way you want to do it. I usually use plus, but people sometimes use minus as well. They both mean the same thing. So now that we have our derivatives, right, how about we start getting all the polynomials. So remember, this is our expansion for the nth polynomial. And we want to do the 0th, the first, second, and third polynomial. So the 0th polynomial, right, we just got the very first term, f of 0, which is just 0. And then P1, we get the first 2 terms, so that's f of 0 plus f prime of 0 times x, which, right, remember, f prime of 0 is just 1, so this is going to be 0 plus 1 times x, so that's just x. P2, now we need to add this n equals 2 term, so we bring down the first 2, and then we add the n equals 2 term, and that simplifies to the right. The first 2 terms were just x, and then this next term, right, remember that f double prime of 0, all the even ones are 0, so that's just 0, and then so that's still just x. And then P3 is gonna be, right, everything we had in P2 plus the n equals 3 term. So I'm gonna stop writing it because hopefully you understand that now. Alright, so P2 was just x, and then f triple prime of 0 we got is -1 over 3 factorial times x cubed. And then P4, we don't have to do P4, but we already have the 4th derivative, and I feel like we haven't seen, right, like we're not seeing a clear pattern here with these, so I feel like we should try to add on a couple more terms to see if we figure out a pattern for the nth polynomial. So however many polynomials you need to try to find the formula for the nth, like where you could see the pattern, that's what you want to do. Like, I personally don't see a pattern here yet. Maybe something similar to what we saw, but I'm not sure. There's no n equals 2 term with 2 stuffs in it. So for P4, we know we take we take P3 and we add on the 4th derivative as 0 over 4 factorial times x to the 4. So we have to bring down P3, which you could just change that to a minus sign. And then we add on f4, remember that's 0, so that's not even going to change anything for us. So P4 is still just x minus 1 over 3 factorial x cubed. So I'm going to actually do P5 to see what happens. So P5 I know is P4, and then I need to add on the 5th term, so the n equals 5 terms, so fifth derivative at 0 times x to the fifth, so that becomes x minus 1 over 3 factorial x cubed, and then f to the fifth, right, the fifth derivative would just be cosine, so that would give us a positive 1. And now we can see a pattern, right? Because now we see that we have like this 1 over an odd number factorial times x to an odd number. Like that's what's going on, right? Because we can see P5 as x over 1 factorial. Wait, let's do it like this. We can see it as, sorry. Wait, this is the game though. You have to rewrite the terms to figure out the pattern sometimes. And we know we have an alternating series, so we know we're gonna need to have, right? And then we also see we have an alt series, so we know we need that for our Pn, right? And so if we want to write this odd number stuff, right, we have to do something like this here. Okay, so basically when we try to write this series, we know we need -1, and we know we want it to alternate, but we want the first term to be positive. So how about we start it at 0? So then if we start it at 0, the first term that we want to see has to have 1 as an exponent. So I'm going to do the 2k plus 1. So x to the 2k plus 1, right? Because for the first term, this will be 0, but I'll get my x to the 1 that I want there. And then I know that I want the factorial to match that, so I want the factorial to have the same expression as the exponent, right? So this is our formula for Pn. So that's the answer for that one, right? So basically, like, sometimes it's a little bit harder to figure out the formula, and you might have to come up with more polynomials, maybe rewrite your terms, but do things like that to try to figure the pattern out. So the last thing I wanted to do was just saying, like, compositions of functions, right? So for example, in the last one, right, I'm recording a video. In the last one, in the last example, I'm sorry guys that I got interrupted. In the last example, for the function f of x equals e to the x, we found around 0 that the polynomial was the sum from k equals 0 to 1 over k times x to the k. And so if, for example, I also wanted to find the function g of x equals e to the 2x squared, then I know that how do I get from here to here is just by plugging in the function h of x is 2x squared for x, right? So g of x is equals to just f with h of x plugged in. And so what I would do is I would just take that polynomial in the same way that I replace the x with h of x in the function, right? Then I would just do that in the series as well. So I would know already that the polynomial for that function is 2x squared to the k. Okay, and same thing for even this last one where we had sine, right? Like if you had sine of x, and we know that Pn is the sum from 0 to n of negative 1 to the k x 2k plus 1 over 2k plus 1 factorial. Right, if I wanted to find the polynomial for some function h of x equaling sine of x squared, I know I'm just plugging in x squared for x, so I can do that equivalently, plug in x squared for x on my series expansion form of the function. So this would be x squared to the 2k plus 1 over 2k plus 1 factorial. And remember, if you have a power to a power, you multiply the powers. So this would simplify as negative 1 to the k, and then 2 times 2k plus 1, that's 4k plus 2. So that's x to the 4k plus 2 all over 2k plus 1 factorial. Alright, thank you guys, and we'll discuss more in class, of course.